All right, today we're looking at topic 2 of Unit 3, which is vectors and matrices, but we're looking at part 2, which is vectors in 3 dimensions. To start us off in our booklets, we've got a review of vectors in 2 dimensions. I'm going to leave this as an activity for you guys to sort of test yourself on the information that we covered last year, just to make sure that you remember all that we covered. So go through, fill in all the blanks, and then check your results with the OneNote. Let's move on to the new content, which is vectors in 3 dimensions. So let K be a unit vector along the z-axis. We've been looking at vectors in the x and y-axis. Now we're adding that third z-axis. And just like with I and j, the next logical letter that we're going to use is K. It's the next one in the alphabet. So a vector from the origin 0, 0, 0 to a point P, X, Y, Z can be written as xi plus yj plus zk. The magnitude of a vector in 3 dimensions is very similar to a vector in 2 dimensions. We're just also adding the square of the z component as well. So let's take a look at some 3D vectors. We've got a 3D plane here. We've got our y, our x, and our z axes. And we've got 4 points here, A, B, C, and D. So we'll list all of our vectors from the origin to these 4 points. So O to A is going from 0, 0, 0 to 4, negative 2, 0. So that is going to be 4i minus 2j. Similarly for O to B, that's 1, 5, 0. So we're going to get 1i, or just I, plus 5j. Then for O to C, we're going to 0, 0, 2. So that's the z direction. We've got 2k. And the last one, point D, which is negative 1, negative 4, 2, we've got negative I minus 4j plus 2k. So those are our 4 points there, represented as 3D vectors. Example 1. Given the point P, determine the unit vector parallel to OP. So O to P by itself is negative 7i plus 3j minus 4k. So unit vector parallel to that is using 1 over the magnitude of OP times O to P. So that is going to give us the unit vector. So unit vector O to P with a hat over it is equal to that there. So if we were to calculate the magnitude of this, it's 7 squared plus 3 squared plus 4 squared, all square rooted. So that gives us 1 over root 74 times negative 7i plus 3j minus 4k. Which if we then distribute it, gets negative 7 over root 74i plus 3 over root 74j minus 4 over root 74k. And that's our final answer. Just underneath this, we have a triangle in a 3D plane, and it's asking us to look at the vector A to B. So similarly to 2D, we would say that A to B is O to B subtract O to A. So in this case, that would be the vector B take the vector A, which is x2 take x1 I plus y2 take y1 j plus z2 take z1 k. Example 2. Points A, B, and C are given as follows. Calculate U, which is 3BC minus 4AB. So BC is equal to 2 take 8 negative 2 plus 7, and 11 take 12. So we've got 2 take 8i plus negative 2 plus 7j plus 11 take 12k. So when we compute all three of those, we get negative 6i plus 5j take k. Right, then for A to B, we're going to get O to B take O to A. So that's going to be 2 take negative 3, which is plus 3. We're going to get plus 2 take 7j plus 11 plus 1k, which gives us 5i minus 5j plus 12k. I just want to check my BC. Did I do O to C take O to B? No, I didn't. So these should all be the other way around. So 8 take 2, 7 take 2, and negative 1 take 11. So this is going to give us positive 6, negative 5, and sorry, this should be 12 take 11, which is going to be plus k. Sorry about that mix-up. So if we then multiply these by the scalars that we're given, we're going to find that 3bc is equal to 18i minus 15j plus 3k, and 4ab is going to give us 20i minus 20j plus 48k. So 3bc take 4ab will give us 18 take 20 is negative 2i, negative 15 take negative 20 is plus 5j, and then 3 take 48 is negative 45k. So that is our answer to example 2. Okay. Two vectors are parallel if one is a scalar multiple of the other, i.e. Vector B is equal to k times vector A. Two vectors A and B are equal if and only if x1 equals x2, y1 equals y2, and z1 equals z2. So all three of these have to be correct for them to be equal. The midpoint M of the line segment is defined by O to M is O to A plus O to B over 2. So we can see that over here. We've got this point M. How do we get there? Well, we take half the direction of O to B and half the direction of O to A, and that's going to get us to the midpoint of that A to B line. So example 3, determine O to M, where M is the midpoint of PQ. We're given P and Q there. So O to M equals O to P plus O to Q over 2, which is going to give us 4 plus 12 onto I plus 8 take 3 onto J plus negative 2 plus 6 onto K, which is equal to 8I plus 5 halves J plus 2K. All right, dot scalar product. We've looked at this with 2 dimensions. By definition, the dot product A dot B is given by A dot B is equal to the magnitudes of each vector multiplied by cosine of theta, where theta is the angle between the positive directions of A and B. So look at the diagram up here, we can see that the tails are joined. Rearranging that, we get that cosine of the angle is equal to the dot product over the magnitudes. And this is useful because we have a second definition of the dot product, which is that A dot B is equal to the products of each, the sum of the products of each coefficient. Since I dot I equals 1, I dot j equals 0, and I dot k equals 0. So if we were to distribute the dot product to A and B, basically when I is distributed to a term that has j or k, that term goes to 0. So all we're left with is the I terms together, the j terms together, and the k terms together, which give us the product of those coefficients. So reminder, the dot product is a scalar. It does not spit out a vector, it gives us a scalar value. The order of multiplication is unimportant. A dot B is equal to B dot A. This is the commutative property. It's also distributive, so C dot A plus B is the same as C dot A plus C dot B. And A dot product with itself is the same as the square of the magnitude, since cosine of 0 is equal to 1. So if the vectors are equal, then the angle between them is, of course, going to be 0. If A dot B equals 0, then the vectors are perpendicular. So let's look at example 4. We've got A and B, and we're told it's perpendicular, so we have to find the coefficient of j in A, which is y. So if it's perpendicular, then we know that A dot B is equal to 0. Therefore, 6 times negative 3 plus 4y plus negative 1 times 2 is going to be equal to 0. So we know that 18 plus 4y minus 2 is equal to 0. So 4y equals 20, which means y has to equal 5. Moving on further, we've got vector projections. We've talked about these before, our vector and scalar resolutes. So if we have this diagram over to the side here, the length of O to A is the scalar resolute of B on A. So this distance from O to A over to the side here is the scalar resolute of B on A. It's how long that line is, and it's given by the unit vector A dot product with the vector B. It indicates how much of B is in the direction of A. The vector resolute of B parallel to A is given by, we draw B with these parallel lines, and it's equal to the scalar resolute that we just looked at, but that then gets multiplied by the unit vector A. And if we're looking for the perpendicular vector, just a reminder for this, we take B and we subtract B parallel. So if we're going from O to up here, to get our A to that point up there, all we're doing is taking B and then subtracting B parallel. So that gives us sort of a resultant there. So that's going to be minus A dot B, A hat dot B times A hat. So it's B take the vector resolute parallel to A. Let's put this into play. So example 5a, determine the scalar resolute of B on A. We've got that A hat dot B gives us our scalar resolute. So A hat is equal to A on the magnitude of A, which is going to be 1 over root 125. So that 125 comes from the magnitude of A, which is 8 squared plus 6 squared plus 5 squared, multiplied by 8i, take 6j, plus 5k. Okay, so If we then take the dot product of that with b, we get 8 on root 125 times by -6, which is our I component of b, plus -6 on root 125, which is our j component of a, times by 2, which is our j component of b, plus 5 on square root 125, which is our k component of a, times -1, which is our k component of b. So then if we compute all this, we get -65 over square root of 125. Okay, looking at part B, I'm actually going to make this a bit smaller. I'm writing at an angle so that I can get the microphone in front of me, but it's looking a bit wonky. Okay, part B. So B parallel is given by what we just found, multiplied by the unit vector A. So we're taking that -65 on root 125, and we're multiplying it by 8 on root 125, I, minus 6 on root 125, J, plus 5 on root 125, K. So that is, of course, our A hat being multiplied by our scalar resolute. And if we expand this out and simplify it, we get 13 over 25, 8i, take 6j, plus 5k. All right, and part C, we're looking for the parallel resolute. So all we do is we have B subtract B parallel that we found up there. So that's going to give us -6i plus 2j minus k, take 13 on 25, 8i minus 6j plus 5k. So that's going to equal -46 on 25i minus 28 on 25j plus 8 on 5k. So that is our vector resolute of B perpendicular to A. All right, three-dimensional vectors in polar form. So when looking at polar form, we initially used theta denoting the angle that it had in the horizontal plane. But now that we also have this vertical plane, we need this second angle here. So this is called the altitude angle, and the other one's called the azimuth angle. That comes from terminology that essentially means horizontal angle, and it's often used in like longitude and latitude looking at a sphere. So theta is referred to as the azimuth angle, and then I think it's phi is referred to as the altitude angle. So the polar form of a vector u, x, y, z is given by square bracket r theta, but then we also add in this phi, where r is the magnitude, theta is the azimuth angle, the anti-clockwise angle formed from the positive x-axis to the projection of u onto the xy plane, and phi is the altitude angle, the angle between the line segment OP and the xy plane. So from the diagram, when looking at sine of phi, we've got opposite over hypotenuse. The hypotenuse is r, and our opposite is z. So sine of phi is going to be z over r. Cosine of phi is going to be a over r. Sine theta is going to be y over a. Cosine theta is going to be x over a. And tan of theta is going to be y over x. All of those just come from our SOHCAHTOA. So depending on whether we're looking at the angle theta or the angle phi, we're going to get those 5 different equations there. Okay, example 6. Convert u into component form x plus y plus z. So to do that, we first of all need to find our x, our y, and our z components. So x is 10 times cosine 30 degrees times cosine 45 degrees. So we can see if we look up here, actually, I'm going to note this out. So x is equal to a times, so from this equation here, we can see that x is equal to a cosine theta. But then from this equation here, we can see that a is equal to r cosine phi. So this is going to be r cosine theta cosine phi. Y is a similar case. It's going to be a sine theta, but we know that a is also equal to r cosine phi. So this is going to be r sine theta cosine phi. And then z is just going to be r sine phi. That can just be read straight off there. So now we have those three equations in terms of r, theta, and phi. So for y, we're going to have 10 sine 30 cosine 45. And for z, we're going to have 10 sine 45. And when we compute those, we get that the vector u is equal to 5 root 6 on 2i plus 5 root 2 on 2j plus 5 root 2k. Part B, we're looking for converting a to polar form. So to do that, we need to first identify what is our x, y, and our z. So our x is -12, our y is 9, and our z is -8. So we'll first find our value of r. So if you take those three, square them, add them up, square root them, that's going to give you a value of 17. Our altitude angle is our next easiest solve. So that's going to that's going to represent sine of phi is equal to -8 on 17. So that's coming from these equations up here. Sine of phi equals z on r. So then if we compute phi from that, that is going to give us -28.072 degrees. Our azimuth angle, we're going to find from tan of theta is equal to y on x, which is 9 on -12. So if we find the inverse angle of that, that's going to give us -36.870 degrees. Because x equals -12 and y equals 9, we recognize that we're in the second quadrant, so we actually have to do a little bit more with this value of theta. We have to take it away from 180 degrees because we found our first quadrant value, but we need our second quadrant value. So it needs to be between 90 and 180 degrees. So that gives us a final value of a equals square bracket 17, 143.13 degrees, and then -28.072 degrees. We can check our answer here just make some observations about our answer. Because we've got this value of -8k in the start of the question, we know that our altitude angle is going to be negative, so that's correct. And like we said, we're in quadrant 2, so we're expecting our azimuth angle to be between 90 and 180, and it is, so we're all good there. We can do those little checks. All right, and that's all for exercise 2.2. Thank you.